Voice terminology can be bewildering. And just when you think you understand it, the words get used in new ways. And you wonder, wait, do I actually understand this? Things are moving way too fast for you to lose time being confused. So by the end of this video, my goal is to make sure that you're crystal clear on the fundamentals of voice AI and conversational AI. Hi, I'm Zubin and I lead DevRel at Cartesia, where we build voice AI models and agents. So I live this terminology every day. And like you, I had to start with the basics. So I'm going to walk you through 13 terms you actually need to know, grouped by topic, each one taking about 30 seconds. By the end, you'll have a working vocabulary that will help you understand, define, and build your entire voice AI stack. You ready? Let's go. Let's start with STT, or speech to text. This is also called ASR, automatic speech recognition. Now you'll see these terms being used interchangeably, probably even in this video. ASR and STT mean the same thing. When you dictate a text message on your phone, that's STT. For voice AI, this is how the human speech input enters the voice AI system. Speech goes in, text comes out. Next, let's talk about TTS, text to speech. That's the reverse of STT. In TTS, text goes in and audio comes out, typically speech. That's why it's text to speech. When an AI talks back to you, that's text to speech. Now, we've had both speech to text and text to speech for decades, and text to speech especially was a little bit robotic back in the day. Modern text to speech, like Cartesia's sonic models, sounds genuinely human. If you're curious and you want to hear what cutting-edge AI speech sounds like, you can try it out for free at play.cartesia.ai. Okay, let's move on next to VAD, VAD, Voice Activity Detection. This is a small specialist classifier model that's separate from your STT, your speech-to-text model. And the only job of the VAD model is to filter the audio signal coming in. And it does things like distinguish silence from sound or speech from background noise. Now, weak VAD means that you're getting garbage in to the speech-to-text model, and therefore you're going to get garbage out downstream for the rest of your conversational AI agent. Fourth term, let's talk about turn detection, also called endpointing. It's a phrase I'm not a big fan of because it can be confusing for some people. But turn detection is how the system decides, hey, has the user actually finished speaking? Now, it sounds simple, but really it's not. Humans pause all the time. They breathe, they trail off mid-sentence when they think, then they come back, and a good turn detection model will detect all this accurately. Because a turn detection model that's too aggressive will constantly interrupt users thinking that they finished speaking, and that's infuriating. On the other hand, if the turn detection is too slow, it's going to add hundreds of milliseconds of dead air, just pauses, which is just as bad for the conversational AI experience. So good turn detection is one of the most underrated and difficult to achieve things in voice UX. Next, let's talk about Barge-In. That's when you interrupt the AI, and ideally, it just shuts up. Now, we've all experienced bad Barge-In, right? Anytime you've shouted at a phone menu that just keeps going, regardless of what you say, that's because you weren't allowed to barge in. And that's really annoying. Real Barge-In needs always-on bi-directional connectivity in the system. So the system has to detect when you, the user, have started speaking. It also has to detect when you've stopped speaking, which is what turn taking is all about. And it also needs to then immediately detect when you resume speaking and you're barging in, so that it then cuts the model's response speech back to you. It needs to immediately cut off that speech audio stream. At Cartesia, we use an event-driven architecture for exactly this purpose. When the model detects that the user has resumed speaking or is barged in, it sends off an event, and the developer uses that event to then mute the text-to-speech system that's trying to respond. Next, let's talk about speaker diarization. This is the model's ability to identify who is speaking, not just that speech is happening, right? So not just voice activity detection, but actually who's speaking. This distinction matters a lot because in noisy environments, it's going to be really critical if you can tell background noise from the speaker. So think of offices, call centers, hospitals, waiting rooms, airports, and so on. If the speech-to-text model and its surrounding architecture cannot separate the active speaker from the background conversation, everything downstream is going to suffer and degrade. That means transcriptions are going to be suboptimal, which means intent detection is suboptimal. Doesn't matter what you send to the LLM after that, and its tool calls are all going to just go out the window. It all degrades. Bad diarization compounds all the way through the system. All right, now let's talk about voice cloning. There are two types of voice cloning that Cartesia offers. One is IVC, instant voice cloning. You simply prompt the TTS model with a short audio sample, about 5 to 10 seconds, and it's going to emulate your voice. It's like prompting the model to mimic your voice. It's fast, it's convenient, and it's surprisingly high fidelity. If you want to go a step higher, you go for PVC, professional voice cloning. This takes between 30 minutes and 120 minutes of audio to actually fine-tune the model weights. That's what you're doing. Therefore, you get more control and much more professional grade cloning. But it needs that little bit more data from you. IVC, instant voice cloning, is a voice prompt. PVC, professional voice cloning, is a fine-tuning of the model itself. Now, if you just want to go for a quick IVC, it takes less than 3 minutes. Just try it out at play.cartesia.ai. Next, we're going to talk about voice characteristics, and this is quite important because this is about the attributes of a voice. Not the easiest thing because it can be quite subjective and it's often down to preference, even if you can measure and quantify it. Let's first talk about prosody. Well, prosody is a word that gets used loosely. Here's what it actually means: pitch, loudness, and timing. The how of speech, the musicality of it, and not just the what's being said. And it's super important. You'd be surprised how important this is. Look, Johnny bit the dog? Sounds like shock. Johnny bit the dog. Statement of fact. See the difference? Same words, just completely different based on intonation and emphasis. Prosody is how humans layer intent and meaning and emotion onto the language. Next, let's talk about timbre, the tonal quality. It's the adjectives we use to describe a voice. Warm, gravelly, nasal. It's why some radio presenters sound instantly trustworthy and others sound like they're reading from a spreadsheet. Timbre defines the character of the voice, not just how it sounds, but also how it feels. And how it feels determines whether users trust it. So this is not just a soft metric, it's critically important, and it's both qualitative and subjective. Now, let's talk about vocal fry. This one makes me hungry. Vocal fry is that low, creaky vibration, that slight decay of the voice at the end of sentences, and humans do it naturally. Because it's natural to humans, it's important in text-to-speech models because it adds naturalism and realism. Without any vocal fry at all, voices sound artificial. But here's the tricky part for AI model labs. Too much vocal fry in your training data kind of pollutes the data set and degrades the model. In speech-to-text, vocal fry can even be misread or misinterpreted by the model as silence or these weird pops. So the goal of vocal fry is have just enough to sound human and not so much that it breaks the model. Now finally, let's address some terminology around accuracy and performance metrics. RTF, real-time factor. This measures speech-to-text processing speed relative to the audio duration that's being processed. So the transcription speed divided by the length of the audio input. RTF of 0.5 means the model transcribes a 60-second clip in 30 seconds, in half the time. For live conversation, RTF needs to be faster than the spoken word because it must be below 1.0. That's a good thing. Now, if the RTF is more than 1, it means your voice application is already broken for real-time use because it means that the AI model literally cannot keep up with the speed of the human talking. The speech-to-text model needs to work faster than the speech from the human comes out for the system to keep working. Next, let's talk about TTFB, time to first byte. This measures the gap between input text being fed into the text-to-speech model and the model beginning to speak. The gold standard for this is, or I should say was, under 300 milliseconds. Cartesia's Sonic 3 models hit 40 to 90 milliseconds. Now let's just put that in context. A human blink takes about 100 milliseconds. Below 100 milliseconds and a conversation starts to feel pretty natural. Above 300 milliseconds, it starts to feel like you're communicating with the upside down in Stranger Things. Okay, now let's talk about a very common and popular benchmarking metric called WER, word error rate. WER was the traditional benchmark for speech to text. And what it does is it counts every wrong word that the transcript has, literally every wrong word. Now for conversational AI, it could be a vanity metric. Why? Well, if a model transcribes gonna as going to under traditional word error rate, that is counted as an error, even though the meaning is identical. So for conversational AI, oftentimes we use semantic WER, semantic where it's much better because it measures whether the model understood your intent, not whether it hit every syllable and word right. Now that is especially true if that speech-to-text transcription is going to be fed into another general purpose LLM down the track, which are experts at semantic context anyway, so they don't need it to be absolutely literally correct. Your transcription doesn't need to be 100% literal to be 100% effective in a good voice AI system, especially if being literally correct is going to add latency to your system. Well, there you have it. That's your core vocabulary for voice and AI. STT, TTS, VAD, turn detection, Barge-In, Diarization, voice cloning, Prosody, Timbre, vocal fry, TTFB, semantic, word error rate, and so on. Now, these aren't just terms, guys. These are ingredients and personality that give your voice agents their utility. Once you know them, it helps you spec better. You'll ask sharper questions. You'll even be able to debug faster when something in your pipeline is misbehaving. Now, if you want, links to go deeper are in the description. And if you're looking to build something in the voice AI and conversational AI space, then definitely follow Cartesia on X and LinkedIn and reach out. Reach out to me if you want, reach out to any of us. Links are in the description. We would love for you to ask whatever questions you have because, we're always happy to help and to take feedback. Okay, that's it for now, guys. If this was useful, please like and subscribe because we've got much more coming your way. See you around.